So today we reach another exciting point in this lecture about generalized Riemannian geometry. So last time we discussed one ingredient that's kind of crucial, and that is the analog metrics. And today we will discuss the other analog, or the other kind of thing that enters physically important, and that one is something that's called in physics a delta. So this will be something in the background, but anyway, we will just do the mathematical underpinning of that. So let's start by a brief recollection about principal bundles. Okay, so recall. So today we will talk about half densities. That's the moral. So first, let me make a brief recollection. So principal bundles. Okay, so this is this will be similar to how we started the previous semester. That I will be just a little bit faster than normally, but anyway, I just want to say a couple of sentences. So what is a principal G bundle? Probably all, or most of you know. So fixed G Lie group. And then the way you should think about principal bundles, so a principal G bundle is a map of two such spaces. So it's a principal bundle over M, such that each fiber, or with each fiber carrying, okay, fiber means preimage of a point. So over each point, you look at the preimage, each fiber carrying an action of G, which is free and transitive. Free and transitive right action of G. Okay, so free and transitive means that that actually all these fibers are just copies of G, except non-canonically so. All fibers are G, but non-canonically. So we can't just say that it's G itself, because we don't know where the unit would be. But yeah, so and then okay, so this is how we should think about it. There are some conditions, but this will be enough for us. Only locally. We require that this thing is actually a product. Locally P is simply a product. You can always find local trivialization. So this is M, and there is P, and all these fibers, they carry an action of G. Which moves you from one point to another. And between each 2 points, there's precisely one element of G that's translated from one to the other. Okay, so what can you do with such things? Well, many things. We can study connections on those. Although for what we want to do today, I will go in a different direction. So suppose that in addition to group, I fix this extra datum. So I fix a representation. So suppose that I have a representation of G, which is a map. I guess I can call it R. So I have a linear space R. Okay, so representation of group means that I have a map, a homomorphism of groups from G to invertible linear operators in my space. Then I can construct an associated bundle. So then we define the associated vector bundle. And then for a given principal bundle P over M, we can define an associated vector bundle to be the following vector bundle as So we take our principal bundle, we make a Cartesian product with the vector space, so that's R. And then, I guess, how should I, let me maybe put a subscript phi here, by which I mean that this is Cartesian product, model some equivalence, and in the equivalence I declare the 2 points in here, so 2 points up there, so let's say P, and a vector V is equivalent to, so identified using the G action, so G acts on the principal bundle on the right, so I will just denote it by putting a bullet dot G on the right, and here I have I act correspondingly on the vector using the representation. Okay. If you want, this is like a fiber product of. Anyway.
Is it a fiber product?
Yeah, I wanted to say that, but maybe in some sense. No, not in the sense I wanted to say anyway. So let's say I didn't say anything. It's defined like this. Okay, and the claim is that this carries a natural point. At each fiber, you have a natural vector bundle, vector space structure. So this is a vector bundle. So at each given, I have 2 elements of this which project down to the same point. Then I can add them. So you can try to see that from the formula. I guess I can just say that this is a. Okay, let me not go into it. Anyway, so this is kind of a. This here ends the recollection part. Just that we are all on the same thing. Okay, so okay, now examples. Okay, is this clear, or do we want me to do more details? Okay, or maybe probably. Okay, so examples. So the one which we will care about actually for now. Later on we might encounter spinners, but for now, let's just stick to the most basic stuff. So if we fix a smooth manifold M, then we can define P to be the frame bundle of that. This is FR frame, which is simply the space. Okay, so how is this defined? So it's a fiber of at any point is the space of all possible bases of all possible linear basis of the tangent bundle at that point. M. Fiber at M. Okay, so the picture is like this. M. I have this big space. You probably know what the thing is. P is called. To throw in some other words, so this thing is called the base of the principal bundle, and this thing is called the total space. That's the name of these two manifolds. Okay, so the frame bundle is a space. It's really a manifold, such that each point there corresponds first of all to a point at the base, and a choice of a frame, a choice of a basis at the tangent space there. Okay. And the claim is that this is a principle of GLN on bundle, where this thing acts simply by mixing your basis. So if I have a frame, if I have a basis at T then I map it to, I take A matrix in GLN R, so quite instantly, and here is the dimension of M. Then I map it to this. And you can check that this is the right action. Okay, so you know that each two bases are related precisely by one GLN transformation. So that's here. Okay, so now if we start considering different interesting representations of the group GLNR, we recover different interesting vector bundles, and most of them are those that you are probably familiar with. So if you take V to be Rn, then the associated bundle is the tangent bundle. Okay, so this is the vector representation of GLNR, and the vector bundle you get in this way, the tangent bundle. You can do V star, then you get V star M. You can do all sorts of, then surprise, surprise, we get TM tensor which to V star M. So all tensors are just associated bundles to the principal bundle of frames. Now there are other interesting representations of GLN which are actually not constructed out of the vector representation. Those are the ones that we are interested in. So the definition. So fix a real number lambda and M manifold. Then we say that, okay, so then we consider okay, let's say n-dimensional manifold. And now we consider the following representation. Consider the representation which will be one-dimensional. So 1D representation which goes from GLNR into the representation should go to general linear of a vector space. So my vector space in this case I will take it to be R. Okay. This is see there is probably an unnecessary clarification. So I'm using GLN in two notations. If it has two arguments, I mean that it's like the first argument should be an integer and the second argument should be the field. And by that I mean invertible matrices of the field to that power. The second different notation is that if I say GLN with one argument, I mean it's the general linear transformations, invertible linear transformations of a vector space. It just so happens that this vector space now is R. Yeah, right? So incidentally, this is the same as R. Also the same as GL1R. Sorry. Yeah, thank you.
So the first one is GLRN. GLRN.
Yes, that's right. Yeah, yes. Thank you. Yeah. Also, I could write GL1R. That would be confusing. So I decided instead to spend like a minute confusing further. Anyway, so you know what I mean. It's one-dimensional representation, and I take it to be that if I take an element in here, then I take the determinant of A, absolute value, and then I take power of minus lambda. Okay, I mean it's clearly a representation because determinant is multiplicative, and absolute value is also famously multiplicative, and power of lambda is also multiplicative. Okay, and now the I should maybe say that since this course is sort of the general theme is maybe a bit specialized, like it's like generalized geometry is like a very, very concrete thing to do. So I think it might be one of the reasons why I'm going into introduce these objects is that these objects are kind of useful on their own. So even if you're not really interested in generalized geometry, this might be handy to you. Because this actually is interesting in many contexts and important. So, what do I want to say? So, right. So then the definition says that the associated bundle, line bundle, okay, line bundle means that it's a vector bundle of rank 1. Because the representation was one-dimensional. Anyway, the associated line bundle is called the bundle of lambda densities. And I will call it L superscript lambda. And its sections are called, and here comes the surprise, lambda densities. Okay, and there is particular cases of special interest, in which case you usually don't use the word lambda, and then in a special case, if lambda equals 1 and lambda equals 1/2, we just say densities and half densities. Respectively. Okay. Maybe unnecessary point, but anyway. And now, what happens in the case lambda equals 0? Okay. What is this bundle of 0 densities? It's functional, because the representation in that case becomes trivial, and just by, if you wish, extrapolating this, you get that these are functions. So the line bundle that you get in that case is just the product line bundle. And 0 densities is the same as functions on M. Okay, so why is this object exciting? Any ideas?
You can take
Well, some of them. Which
all
ones?
of them.
Sorry?
Yeah, it depends if you want to do L2, then maybe -1/2 or 1/2.
Why? -1/2?
Because two of them, if you want to L2 space, no? Two of them should produce something that gives you measure.
Yes, 1/2 in this context. Yeah. Yes, that's one exciting thing that we can do. Any other things? Martin, maybe?
Apart from integration.
Oh, okay. No, I guess I wanted to point that you can point to the fact that you can use them in VB.
Yeah. Yeah, that's also for integration. But
Yeah, so that's also a very meaningful question. Right? But you can. They are in a sort of dual equilibrium in some manifolds.
Yeah.
The geometry.
so it's like the whole, it's like an opposite thing in like L2. In other spaces, you would like multiply 2 of them to get a 1 density, and then you would integrate that. And in BV, you cut the space in half, and then on the half, it's a 1 density.
Right.
So it's like the opposite.
Good. Thank you. Good. I just wanted to mention that it's also useful for BB. Kind of very important for BB. In fact, I will mention it in a second again.
But is any lambda different than 1.5 and 0 useful, or it's just?
I don't know.
No, I mean, if you ever encountered any different lambda than 0.5 and 1?
Kind of. Yeah.
But with the lambda density transform under scaling with weight lambda, right? So
Yes.
in QFT, it's an operator of weight lambda.
Yes. So, for instance, the stress energy tensor, or the stress energy tensor is like a 2 density on a line. Sorry, quadratic differentials. Yeah. So good. Very good. So okay, now observation. Here. I will mention these things again in a second. I just wanted to, have a good discussion going, which is good. So anyway, one observation is that there is a natural action of you know how these derivatives act on tensors of this type, on like sections of tangent 1, cotangent 1, and all that. So how do they act on? Do they even act here, or like what do they do? And the answer is yes. So the story is that if you have any diffeomorphism of M, okay, and if any diffeomorphism of M leads to an automorphism of the frame bundle of frames M. This is just to say that if I have a diffeomorphism from M to M, then in particular I have an identification between tangent spaces. So if I have vectors, I can push them forward and I can get new vectors. If I know how to push forward vectors, I also know how to push forward the whole basis. So if I have a basis, I know how to map it to another basis. And bases are nothing else, just element of the frame bundle. So any diffeomorphism of M, it leads to an automorphism here, which actually covers the original diffeomorphism of M. And hence, this leads to an associated bundle. And hence, to an automorphism of the associated bundles. In particular, this recovers the known free derivative for like tensor fields, but you also get like derivatives with derivatives of half densities. So in particular, there is a well-defined Lie derivative on lambda densities for any lambda. Okay, but maybe one final remark before more remarks. If we look at again at the definition, and we know that it's in particular, or let's say note. So if we take lambda equals 1 without the absolute value. Okay, so I mean if you take the principal bundle constructed in this way, with lambda equals 1, but without the absolute value, then we recover precisely the top forms. Then we get top forms. H top T star M M. That's why the book, this is just to explain the minus there should be for that reason, so that we recover top forms and not top polyvectors. Okay, good. Now, how do we work with such things explicitly for those of you who like more explicit calculations? So what does this construction mean? If you think about, remember the L lambda was the frame bundle, Tm, tensored with R, model Echelon's relation where frame and number is the same as I would act with GLN on it, and then I would here multiply by minus lambda. Okay, this is the definition. So what does this explicitly mean? Okay, I probably didn't do that. Okay, now I cannot put this further. Oh no, I can. Okay. Interesting. Okay, so if you pick any local coordinate chart, is this clear by the way, or do you have? I will give you more insights into how these things behave and what they are. at the moment this is fine. Yeah, questions?
Oh, sorry, I was a bit confused about the fact that it would be the top forms if I don't take the absolute value.
Yeah, it's okay. So the claim is that the representation of GL and R on let's say so TM should correspond to having, well, I think this to be the identity map essentially. Right. That's where I take the first line there. Then you can ask what is the thing corresponding to wedge top of TM? Let's do TM first. So this thing should be the determinant.
And now for one source, or for different forms, it's the dual, so it's 1 over.
Yeah. So
Yeah, that's why it's inverse. Yeah, okay. Yeah, that was the thing. Okay.
yeah.
But if you write how the leader derivative looks like,
Yes.
lambda densities.
Yeah, I will do it explicitly in a second. I was playing with that before, so the way to present it best. So let's see. Okay, so picking a local, pick the local coordinates. See, which is for those who like local coordinates. Sometimes local coordinates are great. Let's go to the next line. So what does this give me? So we obtain a frame of the tangent bundle given by the partial derivatives. Right? So this is a local frame of Tm. But what is a local frame? At any point, it is a basis. There. So now since I have it in the whole neighborhood, so hence I have a section of the frame bundle. Local section. Okay? So, local frame is the same as the section of this. Then at every point I choose an element in the fiber. And so now I can look here. So this gives a section. Okay, let me call the section somehow. Sigma is a good name, although I want to use sigma later for something else. So give me some.
Rho E.
Rho is E. E is good. Okay. Rho I want to reserve for the anchor. Which won't be used in these days anyway. Or maybe let's see. Okay, so I call it E.
Good, but also S.
Yeah, but okay, yes. But this is my S, and I know that for some people it's confusing.
Okay, how does it look like?
Well, this
No, but this is confusing.
I don't know. It's normal. Yeah, I know. It's normal. Yeah. Okay, so this gives a section of L lambda. How does that section look like? Well, I mean, in terms of that quotient, the section is simply this. Right? So every point on the manifolds, I have a section of this first thing, so I just multiply it with this thing with element here, which is 1, and then I take the quotient, so the representative of that. Sorry, the class.
So that should be E.
Yes. Thank you. I called it sigma in my notes. Does this make sense? It should, hopefully. Okay, so this is lambda. And because obviously I want to have some name which kind of refers to coordinates instead of this kind of silly thing, so I will denote it. I will denote it by okay, this is how I will denote it. Now I will denote like that, so you see this coordinate, there's just top forms. Okay, so as we said above, like top forms are essentially lambda equals to 1, but without absolute value. So there you go. That's the explanation for the notation. Okay, there is more advanced. So thing to remember: if I pick coordinates xi, then I have a natural lambda density, which is, or like I have an associated lambda density, which I will denote like this. Now we will see that this is a good notation. In a second. So, well, actually, let's do it right now. So one thing why this is good is that changing coordinates if I pick different coordinates, obviously I will have a different section. It's a different section a priori. But it will be related by the previous one, related to this one, by multiplying it by determinant of the Jacobian. Wait, there is Jacobian determinant already. Jacobian, sorry, thank you. Yeah, okay. So this comes from this thing. Like if I would take if I would change my section of the frame bubble, my coordinates. But if I would change my coordinates, it would lead to a change of the frame bubble in particular, and the way that reflects itself in change of this guy is I will just get multiplied by this thing. Okay, so this is how things work explicitly if you want. For each coordinate I have a natural section and they transform like this if I change coordinates. Okay, any questions? I see people are thinking, that's good. Or maybe bad, maybe they. It's not confusing. Does this make sense? Is everyone happy about that? Good, okay. So then, one observation is that if I have two lambdas, like lambda and mu, let's say, then there is a natural isomorphism to on the level of line bundles. Any idea why this is the case?
Because it's one-dimensional representations. This tensor product of these two one-dimensional representations is a tensor product.
Yes. So tensor product of if I have a representation which let me say that one-dimensional representation given by determinant to some power minus lambda. By this I mean one-dimensional representation of GLN, and I tensor it with this thing. That as representations there is natural map where you just multiply the numbers, and you can check that this is in fact an equivalent map between representations of GLN. Okay, so GLNR equivariant isomorphism in this case. Isomorphism of representations. Okay, this is nothing too surprising. Like if you have, for instance, in the case above, like if I would take V, then I also have a natural isomorphism between okay, how to write it so it doesn't look silly. Okay, well, no, this will look silly. Okay, no, let's do it. So let's say, no, it's okay. The moral is that each time I have an equivalent map on representations, I have a corresponding map on the bundles. Because the bundles are, after all, constructed by simply multiplying by representations. So for instance, I have a natural map for like, I don't know, V tensor V tensor V to I don't know. V tensor V star tensor V. Okay, well, you know what I mean. Like, I don't know. Okay, let's say V tensor V to wedge to V. I have a map on vector spaces where I just keep the symmetric part. Obviously, this thing lives to the fact that if I have two tangent vectors, I can produce wedge to V. That means. How does that bubble? Okay.
I'm not sure, I'm kind of confused maybe what happens there. So you take just a tensor product of two sections and somehow you get a section of...
Yes. Yes, yes. So it's a because both of them they well, if you want, so I have this thing tensored with a similar thing except I change lambda. I want to map that thing. So what you just do is you just do the you do it over a point. So you just multiply. I guess okay. Probably you fix them to have the same thing in here, and then you just multiply them in here. Okay, I think that's probably more confusing than.
Yeah, I think I can kind of...
Yeah. Okay. Yeah. So yeah, is it? Yeah. It's. Good. So now more fun things. So one special thing about densities. So seems to be used the absolute value operation. Yeah. Any questions? Is it about the how you construct the items?
No, no. It's about the integral bundles.
Okay. So okay. So since we use absolute value, one consequence of that, this is a bit of a vague half sentence. So the consequence, there is a natural half line or half line or subspace of L lambda. So if I take what I mean is if I take this thing, I take this one, modulo the epsilon relations, x equals to x determinant g minus lambda x. So this thing is a well-defined map. This. Yes, okay, yeah. R. So here I take a positive thing, it's the same thing here. So the non-trivial, obviously the numerator one is the subset of the other. The non-trivial thing is that this subspace is actually, yeah, this is preserved with these equivalence relations. It doesn't throw you off, so this is actually well defined. Right, so if I wouldn't write the absolute value here, then I could relate x's to x's which have opposite sign, but yeah. But in this case, I only ever relate two x's if I multiply them by a positive number. So actually, I don't run out. So this is a well-defined equivalence relation there, and hence it sits inside here. So in fact, what this boils down is that there is like a natural subspace in L lambda. At every point, I have, in other words, I have a preferred. I can say how positive densities are. So it's like a natural. I have a line bundle, but it has like a preferred plus and minus direction. Okay, so natural half subspace of positive lambda densities. So, in other words, if I give you element of the lambda density line bundle, you can unambiguously tell me whether it's positive, negative, or zero. Which definitely I can't do in a general line bundle. This of course has some consequences for the topology of the line bundle. So can anyone see what this means?
This is
Yeah, but that's yes, but there is a more common word for. There is an easier way to say it. Oriented line bundles or something. Trivial. So, why does it mean that they are trivial? Why is that? How can we deduce that from the fact that there is a distinguished half subspace?
that you can like group together positive density.
Exactly. So very good. So maybe let me just say one sentence before. Just rephrase this differently. I.e., it makes sense to talk about positive, negative density. I should say that in my work I use half densities very often, so you will hear me say half densities sometimes accidentally instead of lambda densities. I think it happened already. Sometimes, yeah. Lambda densities is the topic. Yes, also, yeah, exactly. So the implication, so thus, in particular, L lambda is always trivial, although non-canonically. No, canonically so. Okay, so exactly that's what I was saying. Like you can, because it makes sense to talk about what it means to be positive to half densities. Then you can just take your manifold. There is a line bundle over it, and you just put some open cover. Over each of these, you choose. Yeah, that's what I want to do, right? Like, what do I want to do?
And choose positive section. And just
Yes.
using partition of unity or something.
Right. Oh yeah, you don't want to be compacted. Okay, yeah, right. So you just over each open subset, you just choose a section. You can always do that, even if the bundle is non-trivial, because locally it is trivial. So locally you choose trivializations, which are all positive, and then you group them using partitions of unity, and you know that like a convex combination of two positive things is still positive. So the result will be non-zero. So, e.g. using partitions of unity. You can see that this is the case. I think, but it's non-canonical. There is not like a preferred. This line bundle is always M times R, but a choice of a specific isomorphism is not given. Like you have to choose a global section of this. So, unless of course lambda equals 0, then in that case it's functions, and functions are trivial. Functions are canonically a trivial line bundle. That's like a preferred identification.
So it's kind of torus or something like to say, when it is kind of like positive numbers but with no privileged origin. It's like
Yes.
Yes.
Yes, that's right. Yeah. So you can see that the positive thing is essentially like a R torsor. Yeah, that's right. Like an R principal bundle. Very good. Okay. Now, next amazing claim. So, what are orientations? So, orientations on M. So note that the fact that these were trivial, it didn't require any sort of orientability. So this is how they differ from top forms. So we know that, if you remember, if you take lambda to be 1, but you forget the absolute value, then you get top forms. And top forms famously are not always trivial. They are trivial if only if the bundle is, the manifold is orientable. So how does this translate here? So in fact, orientations, densities are always, lambda densities are always trivial. That's the advantage of them. But in particular, if you pick an orientation on M, this gives an identification from L1 to the bundle of top forms. This is how, this is one way how these things are related. I mean, it matches in the sense that you know that if the bundle is oriented, then this line bundle is trivial, so it has a chance of being isomorphic or trivial line bundle. So note that here I'm taking lambda of L1, so densities. Or if you have oriented manifold, then densities are the same as top forms. So how do we see that?
Not only with respect to orientation, but even changes of coordinates. No?
Sorry?
You have to restrict your structure group to the GR determinant. No?
But that's what it means to be oriented. That's orientation.
No, I mean, you still have to restrict the transformations, not the present orientation. Okay, maybe it's the same thing.
Maybe I just in this case you have two line bundles, and I'm just saying that they are the same one. There is an answer. There's a natural isomorphism behavior. Yeah. So how does this work? So what do we want to build? So let's go from maybe the other direction. So how does the bundle of top forms look like? So it was the frame bundle multiplied by R. But we moved it out by Px, Pg, and there was determinant. Is there a minus one there? Did I forget the minus one? Yeah. Oh no, there was an inverse. Sorry. This has a minus. Here, sorry, I probably said it somewhere before. There is no sign, because here I'm acting with the inverse of the representation of x. It's px equal to pg and rho phi g minus 1. Unless okay, so we have this guy multiplying x. This is what the bundle of top forms is. Now we want to build a map to the bundle densities, which is the same thing except there is an absolute value. Any idea what this could be? So it will be a map that descends from the map. So I want first of all I want to have a map from numerator to the numerator. But obviously I don't want it to be an identity map because you know, I mean I'm claiming that you need some orientation to make this work. So there should be something that uses an orientation. So any solution? So if I take an element in here, an element which would be pair P and X, I should map it to something. Now I should probably remind you what orientation means. Orientation means that orientations, one way to say what an orientation on manifold is that at every point, I separate my frames into two groups. So the frames, they always have two connected components, depending on the left-handed, what is it called? Whether they are left-handed or right-handed, if you want. Orientation. How do you call orientation? Okay. So So there's frames, they always form two disjoint connected components. And orientation means that every point I pick one of these things and I make it consistently along the manifold. So at each point I have I know what my left-handed frames are and what my right-handed frames are. Okay, so having that in mind, what can I write here? Like, I guess
You can keep the P,
exactly. I don't really can do anything much with that.
and then you can multiply X by plus or minus.
Perfect. So let me say like I want to say it like this. X. Okay, so here I multiply. This is plus 1 or minus 1 if P is, I guess, left or right-handed or whatever handed. Okay, so this gives a map of the numerators. Now, does this map, is this map compatible with the quotient? Is it, what do I need to check? So I want to check that. Yes, so okay, I want to check that. What happens if I have a different, if I act with different color, if I act with G, right? So here I get mapped to PG. Well, I just rewrite this, and the determinant of G times X. Yeah. So what does this get mapped to according to our prescription? In our prescription, what does this get mapped to? Well, the first slope is the same, and the second slope picks a sign. So you get 1 minus 1 to the priority or handedness of PG. And then multiplying this thing that we had, determinant G times X. But what is the parity of the, if I had a frame, P, and I accidentally with the matrix G, then the parity will change or not depending on the sign of the determinant. So this thing is precisely minus 1 the P times sign of determinant of G. Hence, this thing that I get is precisely this thing, and I can combine them, minus 1 to the P, and here I get sign with this, just because that gives me the absolute value of that G. Which is precisely where this thing would get, what this thing would get mapped to. So the action of G on this side precisely corresponds to the action of G here, where I have the determinant. Sorry, the absolute value. And this element is supposed to be the same as this one because I moved out of this relation. Okay, that's how it works. Oh no. It seems that I raised my hand again. Okay, any questions?
Yeah, so
Yes.
in this definition, you consider an orientation to like your oriented manifold still have as all the frames, all the charts.
I just distinguish them which are left and which are right.
Okay. But because sometimes you define the orientation to pick for an oriented atlas, which is a sub-atlas.
Mhm. Yeah.
There you actively throw away half
Yes.
of the charts.
Mhm.
In that way, the map would be on the oriented atlas or the oriented frames, the maps would be the identity, right? Because there's no signs.
Presumably only orientation gives us any changes of in touches. So that's
Yes.
the reduction of
Yes.
classification.
Yeah.
I would just understand if I understood correctly.
Yeah, true. That's right.
It's not very deep.
But yeah, I agree with that. Yeah, okay. Yeah, I guess I was using a different molecular definition where you just keep the same.
Keep the same, but distinguish. Okay.
Yes, but like an extra structure on a manifold.
which tells you whether the frame is positively or negatively oriented.
Yeah.
That's the structure.
But you should be able to build an equivalence between these two definitions.
Yeah, just follow the plus, the positive frames.
Only the positive.
Positive frames and positive changes.
Right.
Right, sometimes you define a sub-bundle of the frame bundle, like which has a group O.
Yeah.
And
This would be like GL plus.
Yeah,
it's a GL plus, yes. So there you throw away the frames that would have a negative.
Yes. Yes. Yes, that's right. Yeah. But you should be able to.
Is that construction done on the frames?
Sorry?
It's like that construction just on the other side. Like you pass.
I guess. I mean, what I would say is that like the thing that changes is if you would take your definition, then the group that acts is GL plus. And from the perspective of that group, this representation is the same as the representation without the absolute value.
Yeah.
So that's why they are the same in that. Yeah, that I agree. Maybe that's just easier to see. Thanks.
If I want to integrate on manifold,
Yeah, we'll get there. We'll get there.
yes.
Yes. Is that the next one? Yes. That's literally the next thing. So, densities, now specifically one density, can be naturally integrated over M. Okay, so here we need that M is compact, or at least, or that the densities are compactly supported or fall off fast enough, or density. So the usual stuff you need, supported, or has fast enough fall off. Okay, whatever. So how do you do this, and why does this work? So,
So do we oriented for this?
no, that's the point. You don't. Yeah. Thank you for pointing that out.
Okay.
Yes. And so how does this work? So if you have a manifold and you want to integrate over, then there's first thing that you can simplify it by saying that okay, actually it's enough to consider coordinate charts. So this is a coordinate chart. So it's enough to tell. First claim is that it is enough for me to tell you that I know how to integrate over coordinate charts, because then I can use partition of unity to integrate the general thing. I have to check if it gives the same result or whatever, but in principle it's enough if I tell you how to integrate in coordinate charts, because then I can extend using partition of unity. Okay. So how do I integrate in a coordinate chart? So in coordinate chart I have coordinates, and any density will look here, and the density will look like that. So there will be density, mu section of L1 will look as follows. So mu, there will be some function, and then it will look like that guy over there. So now I just declare that I want the integral to be, well, the Riemann integral, or Lebesgue. Okay. Now, well, I could have said this for arbitrary lambda density, right? So why do I, this arrow naively makes sense even if I put like over 3. So what makes it special to the lambda 1 case? Exactly, the change of coordinates. So I know that densities transfer, if I change, you know how the integral is supposed to change when I change coordinates. It gets multiplied by Jacobian. So, which is incidentally represents the same how densities transform. So yeah, that's why. Know that there is an absolute value, which is what you have in integrals. You don't have absolute value in the top form. That's why integration over top form is sort of like slightly less well behaved than integration of densities. As was pointed out, integration of densities exists on any manifold, even on like Klein bottle or something. It's like unoriented volume forms. In fact, that's why they're called densities, because you can integrate them.
So they are much better for integration than the top forms.
Yes, yes. It's more natural. Okay, so I'm comfortable with it.
But for like Stokes theorem, do you need the oriented space, or is there some kind of version of Stokes theorem for this unoriented space?
I guess you can still have a Lie derivative, invariant under Lie derivative.
But like kind of,
You don't have you don't have t there, but you have a Lie derivative, which is kind of like the forms. Is that true what I'm saying?
actually.
No, fair question. I don't think there is like well, the thing you have is like invariant under Lie derivative still. For the integral, for the integrand. Okay, so now one further application of this is that okay, so now we know that one densities are special so that we can integrate them. But this also makes one half densities or half densities, as we know, also kind of nice because it means that if we have two of them, we can integrate them because we can multiply them, get a density, and then integrate it.
So maybe the use of 1/3 densities because you could integrate 3 of them. No?
Okay, yes, true, but somehow mysteriously the people more care about bilinear forms than trilinear forms. Okay, so particle Hall densities. Now let's say on compact manifold maybe. Form our Hilbert space. Oh. Okay. Maybe I should be more careful when giving lectures. Okay. Well, okay, but here I just mean that they have an inner product on them. I guess for Hilbert space I would need to take out 2 sections or something, which I don't really want to do. Because I want to have smooth sections. This is a smooth course. Okay, but anyway, Hilbert space in quotation marks. But they have an
inner product.
inner product. Yes.
Just
But I
working
think in quantum mechanics, the wave function is usually isn't half. Well, they always integrate it like after squared, right? So it sort of behaves like I mean, usually it's just a function, but it's also like a thing. I think if they've seen somewhere that it would look like the wave function is a half entity. So
Okay. I guess it makes sense.
Yeah, that's exactly to make out 2, no?
Yeah. Yes. Okay. So the okay. Carry in for that if you want. In that case, I could have also said just on any manifold if I take compactly supported. Okay. In any case, I have 2 half densities. And I map them to multiply them with a density and then integrate it.
And now you do it always over real numbers, or so much that doesn't matter?
Everything. This is a smooth course with over real numbers, unless
All real numbers, no complex numbers.
no complex numbers, unless specified otherwise.
Yeah.
And I didn't specify otherwise, so it's okay. And then now the last remark, the one which I was bothering Martin, so I just wanted to say that this is useful for BB framework. So that's another or how densities are. Okay, so here we need supermanifolds. How densities in supermanifolds are one of the central literal protagonist of the big formalism. Of the, and in this case, quantum big formalism. But since this is just an ad, we can ask Martin more. Okay, and as the last thing, I wanted to give an explicit calculation of these open cities, how to do the big derivatives of open cities. Example of explicit calculation. So in coordinates, I mean. So suppose that we have a manifold and we take a vector field, and we take a Hall density, sorry, density, a lambda density. So we take, how should I call it? How do they call it? E? No, I don't call it. Okay, so this is sigma. Sigma will be section of L lambda, and we know that. Okay, so in coordinates xi, we can write sigma. We can write it as some function multiplying this formal expression, which is like this. Okay, and now I will show you why this is a reasonable expression, reasonable writing, reasonable notation of the absolute value. So let's say we want to calculate what this is, the of our sigma. A leader of that. So okay, so first of all, it's a product. So, well, it stands to reason that this will be just a derivative of the first thing, multiplying the absolute value plus. Well, and this, I will really take it as a power, so I can lower this thing, I can put it down, and then get the absolute value to lambda minus 1, and then I will have the derivative of this coordinate lambda density. Okay. This is more of a suggestive way to, I mean, in any case. So I'm giving you more of like a prescription on how to use the derivative, and one can check that this should give the same thing as if you would do things properly. I just want to justify this notation that it's actually handy to use it. So, okay, oh sorry, there is no at the end. So I have a derivation of the half of a one density. So it remains to say what is the last thing. So what is this thing? Well, and here comes the fun fact. If you have a function of one variable, and you calculate the derivative of the absolute value of that function, and what is this? Well, depending, let's say non-zero, non-vanishing. Okay, so f can be either positive or negative. If it's positive, then well, its absolute value is just f, and hence the derivative is f prime. Well, if it's negative, then it's minus f, and then it's minus f prime. So this thing is just sine of f multiplying f prime. In other words, derivative of absolute value is the sine function, and this is a composition of f with the absolute value. It's not an f. Okay. So now I will just cleverly write this thing like this. Okay? Because sine is the same as absolute value divided by the function itself. Okay, it's beautiful. So now I just use that here. So but for that I would need to know what this thing is if I act on the top one, so without any absolute value. Does anyone know what this is? What is the derivation of this derivative? So if I can act, well, as a Leibniz, in the Leibniz way of all vectors. So if I act on the first vector, I can commute L with D. I get V acting on x1. Okay, so I get D and then V acting on x1, on the coordinate function x1 times the rest. And then I have all the other terms similarly. So what is this? This is, well, this is V1. First component of the vector V. And if I d this thing, then I get partial derivative Vi multiplied by dxi. But because all the other dxi's are already here and I'm waiting with them, it means that only the dx1 term will survive, because all the others are killed by something that follows after it. So this whole thing here, it's only the dx1 term that survives, so it's d1. Right, there's too many pieces there. It's supposed to be 1. Sorry. So the only thing that survives is this thing. And then I get dx1 to dxn. And since I do the same for every other term, it means that in the end I sum them up and I just get this is di vi multiplying my original expression. Okay, so this is how divergences work. So now applying this thing together with that calculation.
So did you just prove that the divergence of vector field is kind of natural operation? Because you can always do it.
Yes, with respect to volume form.
But you used it twice, but probably, yeah, you still used it. Yes. Yeah, you used the volume form. If you change the volume form, you would get different.
Yes, yes, yes. Yes, this is a This is very much related to the fact that I have x's here, the choice of x's. So okay, so what should I get? If I take a derivative of something with absolute value, I should get the original thing, but to get multiplied by derivative of the thing inside divided by the thing inside. The derivative of the thing inside divided by this is just this. So di times dx1 dxn. Okay. This is kind of slightly hand wavy, but hopefully suggestive enough.
Because now you proved that your notation with absolute value kind of, is meaningful, but you didn't really show the derivative of the density from the definition.
Yeah, I can, exactly. Yeah. This was not the.
It's like the motivation for the notation. So.
Yes. This, yeah, you're right. Yeah, I should have stated this. This is more like a recipe. Yes. We use that notation, and with that notation we can calculate this, and then if one had enough free time, one could check if it's actually the same thing.
So this is actually correct.
Fine, I hope so. And what else? So you can check it in the special cases of, like for instance, this. If lambda would be an integer, then you know that if you multiply two densities, then you can always reduce it to like. If you multiply two density and 3 density, you get 5 density. So if this would be an integer, you could always say that this is a product of 1 densities. So that would justify the first step that I do this. Like I would.
And then you can do it for rational numbers.
Yeah, sort of. Exactly. Or I guess you can just think about what the. In fact, I think if you do it properly and you just think about how the frame one will transform them with different morphisms, and I think it will just boil down to the same calculation.
Yeah, probably there should be a way like that, no? Like,
Sorry?
Yeah, there should be a way to calculate it from the definition.
Yes.
So do you write the final formula somewhere? Or?
Yeah, I will do it now because I want to take a consequence of that, which we will need next time. So what's the formula? So f of x is v on f, so the derivative of function f with respect to the vector field. And that thing. To the lambda. And then there is, I substitute this thing back, so I get exactly back my lambda. Yeah, there will be partial vi, and then I get my original density again. Okay, and then there is one simple corollary from this lemma. When acting on lambda densities, we have that a lead derivative. Okay, if I have a vector field and I multiply it by a function, you know that in lead derivative in general you can't take the function out unless you act on functions. In that case, you can. So this is not the C, for lead derivative this is not like a C infinity linear slot. We cannot take the functions out. Then what happens is that you get lambda times V on F. Multiplying your half density. So all of this is supposed to act on a half density. Sorry, lambda density. Okay, does that make sense? So let's prove this. So we can just do it in coordinates here. So let's say I take. Unfortunately, there is two different f's. So okay, but anyway, we will do it somehow. We will manage. So suppose that we are taking. I will use h in the formula as well. Okay. H times this dx1 which dxn lambda. We want to compare this to the lead derivative of the same stuff. H. Okay. So if I act on an arbitrary lambda density, which I here represented by h times something.
You also said before that you need the volume form for the divergence. Makes sense.
No, but the density is enough.
Then so that's exactly my question. So now you kind of secretly use these top forms and so on, but actually all those formulas, because they make sense locally, so they make sense even on a non-oriented manifold.
Yes.
So even the formula, even rolling the divergence, that's also meaningful, I guess.
Yes. Yeah, I can see that maybe the other. Yeah, I think we will be using this later on. Yes, so I will talk about it again. So you're right, like you can define divergence with respect to a density just as you would like lead derivative of the density divided by density again.
Of any lambda, or is the some special?
No vanishing density.
Yeah, but the lambda can be anything.
It could be, yeah, but you can always multiply by some power to make it total one density.
Yeah, but
so for instance, natural notion of a divergence with respect to half density, I would say that we take the half density, square it to get the density, and then you define divergence. And that's what we will do. So, okay, so far let's just calculate this. So if I use that formula above, then essentially I want to check if I can take the function out. So I now substitute this formula, except that if for f I have h. Sorry for that. So you see that the first term here is C infinity linear in v. Okay, so if I would instead have f v here, and I can take the f out. Imagine, of course, that this is h. So the first term I just, there's no problem in there. So the only thing that happens is, so I can focus on the second term only. So what do? I want to write this term. I want to write it once with f times v and once with v. And I'm multiplying some, that's it. Yeah. So this thing is lambda. In both terms, this thing and this thing stays the same. So I have f times double lambda. H. But I need to look here. And in one instance, I have there this one, this thing, and in the other case, I have this thing. And so what is this? By product rule, the thing that survives is partial IF multiplying VI, which is otherwise known as vector field V acting on F, which is what we wanted to show. With derivative of this minus F times the derivative of that acting on anything returns the same anything multiplied by lambda VF. Yeah. And you can compare this. If you want, you can check this. You can compare this with volume forms. Like it's the same thing for top forms. If you have top form, and I would do this thing, then I precisely get 1 times VF, which shows, as you said, the top forms are the same locally as volume forms, so as densities, sort of. So yeah, so that closes the part on half densities. So I think we have 5 more minutes, but I think it's probably maybe we can stop here. And so next time we will do connections, and then we will get to curvature tensors. So any questions? Well, if there's no question, let's make one more definition to build the same. So take sigma to be an everywhere non-zero half density. So then we define divergence with respect to sigma, diff subscript sigma, to be a map from, and actually, sorry, let me do this already in the Courant case. So take E over M to be a Courant algebraic. And now I define an operator that goes from section of the Courant algebraic to function on the base manifold. And I define it by saying that if you give me this function U, as a section U, then I take this to be, I take the anchor map, take the lead derivative with respect to the anchor map of U, so I map it to a vector field. Then I take the derivative of the corresponding density that I get, so sigma squared, and then I have sigma minus 2 to make it. This is how I would normally, if I would not have sigma, but I would have a density, a proper one density, then I would take the derivative of the density and I would divide by the density. And I can do that because there are non-vanishing forms, non-vanishing sections of a Weidmann group. And okay, and then maybe the immediate dilemma is that if I multiply my section by a function, then I can it's not just taking the function out, but there will be an extra term which is given by a rho U acting on F. And let me prove that. Yeah, sorry, probably you had a feeling that I was going to end. We still have like 4 minutes. We aren't going to waste it. So, okay, let's see if we can do this. One of these proofs where you just calculate. So this is sigma minus 2 Lie derivative of this guy and sigma squared. In fact, okay, whatever, times f sigma minus 2 L rho sigma squared. So what do I do now? I put them together. So sigma minus 2, and here I can write this as the Lie derivative of f and the row of u, okay, because the anchor map is vector bundle map, so pointwise I can take multiplication of by a function out, and I compare it to this one, and now we are precisely in the frame, and this acting sigma squared, and now we are precisely in the frame where we have been before, that we know that's the previous lemma. So this thing is precisely the lambda, which is 1, acting on v, so this is rho u on f. As a function multiplying this, so I have sigma minus 2 and sigma to cancel, and I end up with what I wanted to. That's the end.
Sorry, you say that this would work with every lambda, just replacing 2 by 1 over lambda? Or
Yes.
okay.
Yes. It's just that for reasons that are not clear at all at this moment, later on we will exclusively work in power densities.
Sure.
Can I just ask clarification? So sigma minus first power, for example, how is that?
Yes. So yes, good question. So, okay. So various types of answers are possible. One of them is that sigma squared is non-vanishing everywhere. So you know that if I take this thing, which is again a density, it should be proportional again to sigma squared. Because it's a line bundle. That is, if I have non-zero section, then everything else is a multiple of that. This thing will be, some function multiplying sigma squared. And this is a unique function, and this is what I would call that. Like the definition of this object is that.
So it's a formal inversion.
If you want.
So it's not a minus 2 density.
Well,
But sigma is a 1/2 density, so this would be minus 1 density.
yeah. So this will be one answer. Kind of avoiding the question of defining sigma minus 2. The other question, the other possibility would be to really say that it's a minus 1 density because you have this multiplication, and you can use it. If you have, in particular, you have a map this to the trivial line bundle times n. So you can always. You have inverses, like there is an inverse of an element in here if it's non-zero. Because this is like one-dimensional. If you have to point-wise, this is like one-dimensional vector space and another one-dimensional vector space. And in other words, if you have a vector space, which is one-dimensional, and you take an element which is non-zero, it's like a frame in that vector space. So you can take the dual frame, which is an element, which is a dual. Element, it's a frame of the dual space, but dual, in this case, it's an element of the dual space.
The L minus lambda would be the dual of L.
Yes, yeah. The point, yeah. That's true. And, yeah.
Okay, so is that general? Can I write down like L lambda dual is L minus lambda?
Yes, that's true, yeah. Yeah, maybe I should have said that as one of the properties. Yeah. Yeah, maybe this is a good property too.
Next time.
Okay. Yes. So yeah. Thank you. Yeah, that's true. Yeah. The reason is that there is a pairing to the trivial model.
So, can I just clarify? So, should we already see how this relates to the dilator? Because I know.
No. Not yet.
No.
So the relation will be that if you have a metric already, by some reason, then you have an associated metric Hall density, and you can compare it to your Hall density. So if you have a sigma, then you can write your sigma as like this metric Hall density times some function, and that's the real. This will appear later. Well, all depends on how you define the Dalton. I mean, typically physicists say that Dalton is a function, but like you can argue that maybe it's more proper to actually see Dalton directly as the Hall density. Some people do it that way because it's the thing that anyway multiplies the direction function.
Okay. So we are going to deal with this stuff later.
Yeah. I know that I said at the beginning that there is Dalton appearing, but well, in a hidden way. Okay, thank you. Good questions.